E over FQ. And so what I want to discuss today is complex analog of the Riemann hypothesis of the last Weil conjecture over complex numbers. So, so the story is the following. So we have x0 over fq, we have x, which is x0 under fq bar, and then we have the Frobenius map acting here, and we already discussed that the first two of the Weil conjectures follow formally from the analog, from the existence of reasonable cohomology theory, namely cohomology theory that satisfy that has Lefschetz formula for the number of fixed points and the Poincare lines. Namely, so if you have the Lefschetz formula, then this number, the number of points on x0 over a finite field, can be expressed as sum over all I, greater or equal than 0, of traces of the Frobenius acting on this homology theory, which we'll still have to define, on x, right? Minus 1 to the power of. Okay, so let me recall how it follows the rationality. So if you denote by alpha I eigenvalues of the Frobenius on even dimensional homology and even degree homology, and by beta eigenvalues on odd degree homology, then you can rewrite this trace, right? So you have eigenvalues alpha 1, alpha s. These are eigenvalues that come with positive sign, and you have also some eigenvalues that come with negative sign, and that's so there exists some complex numbers such that for all n we have this formula. And again, this alpha I and beta j are just eigenvalues of f acting here. Very good. And it follows that by straightforward computation, the zeta function of f0 then is equal to the product of 1 minus beta I t, where I goes from 1 to r, over the product in 1 minus alpha j t. Very simple formula. Okay, so so this is rationality, and now the last Weil conjecture is about absolute value of zeros of this zeta function. It asserts that the absolute value are of the form q to the some integer from 0 to dimension of my variety divided by 2. So so the Riemann hypothesis, the last Weil conjecture, is a statement about the eigenvalues of the Frobenius acting here. Well, let's see here. So I haven't yet assumed that x is proper, so for any x, this formula holds for any x, even singular, but then you need to put homology with compact supportive x is proper or projective, then this is usual homology. So the Riemann hypothesis is for homology for projective or smooth projective varieties. So, and it's equivalent to the following assertion for smooth projective x eigenvalues of Frobenius acting on hi of x have norm. These are complex numbers, algebraic numbers have norm q to the power I over 2. So in this formula, this eigenvalues we are talking about this alpha I and beta j. So we recover the wave conjectures from this. So that's what we will eventually prove. But
wait, so norm is in below 1 or?
well, so this is an algebraic number. So you can embed it into a field of complex numbers in many ways, right? But for all embeddings, the complex absolute value, this is the, by norm I mean just the absolute value of the complex numbers,
So
right?
not what people call the norm of an algebra.
Okay, so absolute value. Okay. So very good. So whereas this formula, at least it has an analog. It's kind of something that we would expect from a reasonable homology theory, just from, well, because we know this in algebraic topology. This result here seems, well, it doesn't have any analog in algebraic topology. It's kind of deeper. And nevertheless, it has an analog in complex algebraic geometry, and that's what I want to explain. So let's start with the following baby example. So let's prove the theorem. So suppose first that x is a curve. Smooth proper. And suppose I have any map from x to x, and its degree, suppose that its degree is some number, need not be power of prime, just notation. Then eigenvalues of Frobenius acting on homology, usual basic, well, it's homology with complex coefficients. So hi of x with this is the basic homology of the underlying topological space, not the risky homology, classical homology. Have absolutely value q to the power I. So let's prove this. Well, first of all, even to make sense of this assertion, we have to know that these eigenvalues are algebraic numbers. Why are they algebraic numbers?
Because you can write q instead of c.
Very good. Because this has a rational structure, right? This is h I of this is homology of topological space with complex coefficients, and you can write it as h I of x with rational coefficients tensor C. And any map from x to x induces a map in the space. So, and then eigenvalues, well, they are zeros of characteristic polynomial that has rational coefficients, and therefore they imply that eigenvalues are algebraic. Right? Not just arbitrary complex numbers. Does it make sense?
Yes.
Okay.
But why do we need them to be algebraic?
Well, that's this is a good question, but so if you wish, this is a part of the Riemann hypothesis. So it will be highly non-trivial in our setting, but in this setting it's trivial. Now, what are the dimension of the homology groups of a curve? Smooth projective curve. What is H0? One dimension. And F, of course, well, it's just constant. So we assume that the curve is connected. So what is H2? 1. And how the Frobenius, how this map, sorry, it's not the Frobenius, this is just any map from X to itself. How does it act on the degree 2 homology?
By multiplication by t?
Yes, by degree, that's definition. So at least we know the result for I equals 0 and 2, right? So now let's try to prove it for H1. And this is already non-trivial because it's not true if you replace F by C infinity map from X.
Еще раз, для И равно двойке у нас...
Одномерное пространство.
Да.
А что такое степень отображения? Степень — это то, как она действует на стадии.
Получается,
Very good. So for H0 and H2, this is of course true for any C infinity map of degree Q, where the degree is defined precisely as the number it acts by on the top degree homology. But for H1, well, you can easily find. I will leave it for you to find. But for example, you can take an elliptic curve, which is topologically a product of S1 times S1, and find the C infinity map from S1 to S1 that doesn't have, well, this absolute values on homology do not satisfy this formula. So this is deeper, and so let's prove. The proof is interesting, and we'll generalize it.
Сейчас, можно вопрос? Я чуть не поняла, в смысле, а почему нетривиальность в И равно единичке? Ну, я просто аргумент не поняла.
Почему это нетривиально? Okay, so I will give you an example. So suppose you take, let's take elliptic curve, right? So it's as a topological, what is an elliptic curve? It's a quotient as of C by lattice. So let's take for the lattice, well, let's take just for the lattice Z squared, sitting inside Z. C. Then this is, well, as a topological space, it's, okay, so we have this. And now let's try to see what we have. So let's consider, so let's write it as S1 times S1. Then consider F, which is a map from S1 times S1 to itself, which takes point Z1, Z2 to z1 to the power n, z2 to the power n. What is the degree of this map? What? So you need to see how it acts. So z here is well, we identify S1 with complex numbers of absolute value 1, then the form is, so let's look how this, let's see how this map acts on the generator of the top degree homology group. This is Z1 over Z1, this is the form on S1, which gives a non-trivial class, and I take Z2 over Z2, and what happens if I take the pullback of this form under my map F? What happens if I take the pullback of this form under the map that takes Z1 to the nth power? Okay, so this is n times m times dz1 dz2. So the degree is equal to n times m. Okay, and what are the eigenvalues? So the first homology group has a basis formed by this class and by this class. And these are the eigenvectors. One is multiplied by n, another is multiplied by n. So if n is not m, we are in trouble. So we want to show the assertion is that the absolute values have, so the eigenvalues have absolute value square root of this number. Right? So, maybe I will, so let's see.
Почему, какое дополнительное условие на теорему, чтобы такого не было?
That's a good question. So eigen values on H1 are n and n. So, and q in our case is m times n. We want the eigenvalues have absolute value square root of this number, but instead we have the two different norms. So yes, so why it's not a contradiction? It looks like a contradiction. Definitely. Yes. So this map is not algebraic. Need not be algebraic, right? We started by decomposing an elliptic curve into product of two circles, right? So this is just the C infinity.
Это not algebraic on C.
Yeah, it's not, well, let's say algebraic here means the same as complex analytic. Any complex analytic map from a smooth projective curve to itself is automatically algebraic. But this need not be even complex analytic, right?
This is just real analytic.
Real analytic, right? Exactly. That's the problem. So that shows that the theorem already in this case is non-trivial. So let's try to prove it. So so we are looking at H1 of x with C coefficients, and we have the Frobenius, right? So we want to construct. Well, we want to show. We want to estimate the eigenvalues. So what are the structures that we have? First of all, we have a skew-symmetric pairing, the point-correct pairing in H1, right? If you have two classes in H1, you can take their product you get a class in H2, and H2 is identified, canonically identified with C. So you have this F, well, it preserves the skew-symmetric pairing. Well, not preserves it, the skew-symmetric pairing gets multiplied by this degree, by definition, because it's how it acts on H2. Right? So in other words, if I take this guy and divide it by square root of Q, then the skew-symmetric pairing will be preserved. Right. So I have a map from H1, H1 is C, tangent C. We're using C, which takes alpha, tensor beta, well, to integral of x of alpha times beta. And if you so let's see how this form transforms, how f respects this form. If you consider this, compute this form on the pullback of some classes, alpha and beta, this is equal to integral of x of the Frobenius alpha times beta. And so this is degree 2, this is degree 2 plus in the rank homology, right? And by the very assumption, by the definition of degree, so this is equal to, well, it's my f acts by multiplication by q, the degree 2 homology. So this is equal to q times integral of alpha, right? Good. So in other words, if I in this formula replace f by f over square root of q divided by square root of q, the form will be preserved. So I have a vector space, there's a skew-symmetric form, and I have an endomorphism that preserves the skew-symmetric form. What can you say about the complex, the absolute values? Well, it's just a symplectic. What can you say about eigenvalues of symplectic endomorphism? Well, even if your space is, say, two-dimensional, the only conclusion that we can make is that the product of the eigenvalues is equal to 1, right? So, saying that on a two-dimensional space, an endomorphism of the two-dimensional space, of a two-dimensional space preserves skew-symmetric form, it just means that it preserves it has determinant 1. Right?
То есть ты говоришь, что тебе косимметрично не хватит, а вот Келлеровой хватит.
Да. So this is not good, and the example that we have over there shows this exactly this situation. So if I divide this f by f star by square root of q, well, the eigenvalues will be n over square root of q and n square root of q. So the product is 1, but that's all you can see. So that's not good. But the idea is the following: that in addition to this skew-symmetric pairing here, you have a Hermitian form on this space, which is preserved by f of a star. So let's define this Hermitian form first. So I will denote it by this will be my form, and it's f beta goes to just this. Well, it's not yet Hermitian. Okay, so let me do this computation. So this is definition. So I will define this form by this formula. So what is beta bar here? Again, this is a complex vector space, but it has a real structure coming from here. So it makes sense to take the complex conjugate. And now, let's see whether it's Hermitian. Hermitian means that it's linear, complex linear with respect to the first argument, antilinear with respect to the second argument, which is okay here, right? But it also must be, well, not symmetric, but, we need to check that alpha beta is equal to beta alpha bar, right?
Мне сказали, что звук не пропал.
Я включила уже. Вот, сейчас спрашиваю.
Okay, so so let's see. Let's prove this. So
Да, Вадик, еще положительность надо не забыть.
yes. So okay.
Ты не докажешь.
So let's see what we have here. So so if I interchange this, that will be the same as integral over. Well, I can take the complex conjugate alpha bar beta, and then this. Yes, very good. So, and it doesn't work because it's negative beta alpha bar. So that's what we proved, that this number is equal to this number. Is it clear why you have this this negative sign here? Because да.
Да, хорошо.
Good. So so it doesn't work. So it's not Hermitian, but I can fix it by putting factor I. Then okay. Then it will be negative I. Okay.
Да, но извини,
No, so I do right.
тебе же даже и подправлять, в принципе, ничего не надо.
Okay, no, I.
Нужно от собственных векторов ее взять и все. Но это твое право, конечно.
Okay. Yeah. So we have this Hermitian form, and as Volodya mentioned, if it were positive, right? If it were positive definite, we would be done. So it's clear. So what we have, we defined a Hermitian form, and it's clear that f rescales this f upper star alpha, f upper star beta is equal to q alpha beta, right? Just by definition. And so in other words, if I divide f upper star by square root of q, it would preserve this Hermitian form. So
Но мы же еще не проверили все-таки вот эту условие.
вот это
Да.
проверили.
Как? Потому что поскольку мы умножили на i.
Да. То есть, если без умножения на i, она даже просто в точке. Sorry, if you without this factor, it's not even real when you log when beta is equal to alpha. So it's we can't even. Okay, so if I have a matrix, if I have a linear automorphism that preserves a positive definite or negative definite Hermitian form, then by linear algebra, I know that its absolute values are all equal to have absolute value. Its eigenvalues have absolute value 1, right? Absolute values of a unitary matrix have absolute value 1. Shall I prove this? Oh, it's okay. I hope that everyone can just use that condition. Okay. So that's, but we know that this cannot be the case because after all, well, all we use here is that we have the real structure on this space and F preserve this real structure. But even in this example, well, we could do the same thing. So far, we used only algebraic topology. So that means that this form cannot be positive. Otherwise, we would get contradiction. And it's not positive. So that's the problem. However, we are going to see that this space canonically splits into direct sum of two spaces. And over one space, it's positive. On the other space, it's negative. And any algebraic map from X to itself preserve this decomposition. Разложение Hodge, да. So that's the main idea here, and let's realize it. So I will erase.
А можно у вас поправить только немножко?
Да.
Ну вот в исходной формулировке там нужно, чтобы у f была степень q в степени m, либо в утверждении должно быть знаменателя n.
А что такое n?
n размерность.
У меня размерность кривая у меня.
А, и кривой, понял.
Да.
Ну, в смысле, это для любого.
Сейчас мы давайте мы чуть-чуть по порядку. Значит, давайте для кривой докажем. Okay, so we work again. So the idea is to show that this has a decomposition, canonical decomposition, preserved under any algebraic map.
So what we obtained so far is that our form is conjugate symmetric, linear
Yes.
in the right way, but it's indefinite, right?
Yes, it's indefinite. Is indefinite. Even in that case. So okay, so let's correct this. So let's consider the RAM. Well, this first homology. So I can think of this as the RAM homology of X. This is H1 of its coefficient. This is the RAM isomorphism. And so what is this? This is the space of closed one forms, C infinity one forms, modular exact one forms. And in particular, I have holomorphic one forms. Right? So every holomorphic form is automatically closed because there are no holomorphic two forms on a curve. Right, and it's known that so I have a map from global one forms to H1, and in fact this is an embedding because if a holomorphic form were exact, it would be differential of a holomorphic function, but every holomorphic function on a proper curve is constant. So that means that this is an embedding, and I want to give a name to this. This is F1, and I'm sorry that for this, my F stands for the map, but we'll have indices. So this is the first term of the Hodge filtration on this guy. So now Hodge decomposition in the case of curves is the following assertion. So I have this subspace here, so this is subspace in this complex vector space, but this complex vector space has a real structure, right? This one has a real structure. It's Betti homology with real coefficients, tensor with C. So if I have a subspace, I can complex conjugate. So I have another subspace, and they both map to H1, say text C. And Hodge theorem asserts that this is an isomorphism. So this space has precisely half of the dimension of the. It's this has dimension 2G where G is the genus and this is G. And they are kind of it's maximally non-real subspace, right? So okay, so let's now claim.
Извините, как вы доказали, что любая голоморфная форма замкнута?
Просто два форм голоморфных нету.
Но может быть дифференциал не голоморфный.
От голоморфной функции, ну как, если вы берете...
Форма.
Нет, ну как, если вы берете, это называется условие Каши Римана. Если вы... Если хорошо, df под z с чертой равно нулю. Okay, so now what I want to show is that f1 and f1 bar are orthogonal. And if I take this form and restrict it to f1, then it will be, I think it will be positive. Yes, positive. Definite. And restriction to f1 bar is negative. Okay? So that explains why this form is indefinite. You have both positive and negative signs, but it solves our problem, it proves our theorem. Once I know the claim, because this decomposition is natural with respect to any map, that algebraic map, because any algebraic map, any holomorphic map, definitely pullback of holomorphic form is holomorphic. So it preserves this subspace F1, and therefore it preserves this subspace. So any holomorphic, any FF star preserves this decomposition. The spaces are orthogonal, so on each subspace I can look at the eigenvalues, and I know by the linear algebra result that the eigenvalues have the correct norm. Does that make sense? So let's prove the claim. So I take alpha in gamma x omega 1. And what I want to estimate is, I want to show that I times integral alpha wedge alpha bar is greater than 0. Alpha is not 0. Okay? So let's do the computation. So I claim that this will be a positive multiple of the volume form. Right? So I have, okay, so any complex manifold is orientable. Right? So pick any volume form compatible with this orientation. Then I claim that it will be a positive function times this volume form. And therefore the integral will be positive. This is a local computation. Local. Our alpha is f of z times dz. So alpha wedge alpha bar is is f of z squared, which is good. It's positive, times dz, that's dz bar. And so you can compute this and find that this is equal to negative I times f of z times dx dy. And this is positive in the sense that, again, it's so orientation is what is an orientation of a manifold? It's kind of the positivity, notion of positivity for top degree forms, right? So, okay, so it's positive. Because our orientation on, as I said, every complex manifold is orientable, is oriented, and the orientation is constructed as follows. So if you have, holomorphic coordinate, say in this case it's just z, then its real part and its imaginary part, in this order, x, y, is the preferred canonical orientation of the complex manifold. So that's kind of the positive form. If you choose another coordinate, this guy gets multiplied by a positive function. Good. Да, абсолютно. So this proves the claim, right? So you multiply it by I, you get positive. And so this proves this claim, and the second claim, form of alpha. So we also need to show that this is negative. But if alpha is as before, then alpha bar, which alpha bar is what? It's how can you compute it? It's it has so this is negative alpha. Okay, this follows from there. So you get negatives. So the claim is proven, and therefore
We haven't proved that they are orthogonal.
they are orthogonal, right? So why they are orthogonal? So what you need to show is that so we prove this and this. We need to show that if alpha is say alpha and beta I f1, then integral of alpha dash beta is 0. Right?
Нет, доказать, что интеграл альфа-бета 0.
Сейчас, да, вот так.
Ну да, есть.
Okay, yeah, thank you. So this implies that F1, that's equivalent to say that F1 is 0. And this is obvious because these are holomorphic, so when you just multiply two holomorphic forms, you get 0. There are no two holomorphic two forms. Right?
Извините.
Да.
Это равносильно тому, что f1 и f1 сопряжены 0.
Да,
Как раз.
да.
То есть даже не просто интеграл равный, а в принципе...
Форма, да.
Но это же часть равномерения, это не сложно.
Да. Хорошо. Good. So again, so the argument now is completed because we have F1, we have F1 bar, and we have f upper star acting here, and it also acts here, and so if you divide by square root of q, and here by square root of q, these are linked. That's completed. Good. So let's try to. So this this is the case of curves. Now I want to explain a generalization. So okay. So.
Сейчас, а как вы доказали теорему?
Ну а что? Мы доказали, что собственное значение Фробениуса, значение f по модулю равны корню.
То есть вот когда у нас унитарные,
Да.
они по модулю единицы,
да.
и из этого...
Да. Eigenvalues. Of norm 1. Good. So let's try to generalize this. So what do we have? So now we have x over c, and it will be smooth projective. Smooth projective. And the same question. So let's say d is the dimension, complex dimension. So suppose we have f, which is a map from x to itself, and suppose we know this degree. Degree f is q. What are the degree? It's how it acts. It means that, by definition, it means that, well, the top degree homology group of x is still one-dimensional. So f defines an endomorphism of this one-dimensional space, and by definition, this endomorphism multiplication by it. So, okay, so, and we want to, we would like to show that the eigenvalues of f on, we want to look at f upper star acting on homology group homology group I of x with c, and we want to show that the eigenvalues have norm absolute value q to the I. Well, unfortunately, this is yeah, maybe.
Должно как-то зависеть от размерности.
Yeah, very good. So a reasonable conjecture would be that when I is equal to 2d, I'm supposed to get q. So what should I put here? I think it should be I 2d, right? So right. Thank you. But unfortunately, it's still false. And I will give you an example. And it's very similar to the situation that we had for C infinity automorphism, endomorphism of an elliptic curve. So let me give an example here. So let's take our x will be p1 times p1, and I will take map f, which is sort of given by f and g. F and g are maps from some maps from p1 to p1 in an algebraic form. And assume that degree of f is n, degree of f is of G is m, then degree of f is equal to what? So the fourth degree homology group of P1 is the tensor product of the second degree homology group of P1 of this copy and second degree homology of this copy. So in this tensor product, f, this capital F, acts as n times n. Right? So now on the other hand, H2 of X is H2 of, by the current formula, it's H2 of B1 and plus another copy. And so F upper star here. So these are one-dimensional spaces, right? And so how this capital F acts on this one-dimensional space? It acts by multiplication by n here, and also, so it's given by this matrix n. So the eigenvalues are n and n, and we are again in trouble.
Но если Taylorов класс собственный, то никакой проблемы вроде нет.
Yes. So the kind of the solution was invented. Well, so it's like Sarah who realized that you can correct it by requiring more. It's not enough to know just that the degree is equal to Q. So remember that our X is projective. So so it sits inside a projective space, some projective space. And so what I want to assume instead is that so my endomorphism F is projective. Or it's equivalent to saying that F, F upper star. So it's projective it comes from, by restriction, from an endomorphism of this guy. So, well, it's equivalent to saying that it preserves all one. So if I have a projective variety, then it comes with an ample, very ample line bundle. And the condition is that the pullback of this is of Q, right? So just remember that this condition is obviously satisfied over a finite field when F is a Frobenius, because the Frobenius acts here, and my O1 is by definition is a pullback of a line bundle on Pn. So what is O1? Is the sections of O1 are functions with a simple pole at a hyperplane. If I have a function with a pole at a hyperplane, when I take its fifth power, it will require a pole of order q, right? If I take its qth power, sorry, right?
Sorry, what?
So the claim that I want to make is that that's a remark. That if I consider the Frobenius on the projective space, n over Q, then the Frobenius pullback of the divisor of the hyperplane given by the hyperplane by a hyperplane n is equal to Q times this.
Ну просто Фробениус путаю сильно.
Да. Да.
Сейчас, можем написать.
Нет, это было такое замечание, что это условие, что у нас вот это вот выполнено, оно естественно возникает в характеристике.
Да.
Ага, хорошо. Okay, so then the claim is that it's still true So I need to correct it. It means that then I need to erase it. It's not. So if I have this property, then it follows that the degree of this map is q to the dimension of my scheme. So that's why I need to erase it. Okay. So that's what we're going to prove. This is theorem. And this is a non-trivial theorem. So, смотри.
В смысле, есть стабильный пучок на x, который...
Да. Значит, вот если верно такое, то степень f равняется, это вот условие означает, что степень v of f is equal to q to the n.
Давайте, может, просто обозначение не очень понятное людям. Ну, что O от единицы от x надо
Нет, ну это все понятно.
Ну хорошо, на x. Okay? So, why that? So there is every line bundle has a class, a Chern class, which lies in H2. And if you take its degree d power of this class in H2, you get a generator in the top degree homology group. So that means that if my f multiplies this class in H2 by number q, right? So this formula in particular implies that the first, that the Frobenius, or that f upper star of the first Chern class, which lies in H2, is equal to q times itself. And it follows that on the top degree homology group, the action is by this number.
Нет, ну хорошо, но почему нормы у нас теперь и пополам?
Ну, было вот так.
Все, хорошо.
Ну, а теперь мы переобозначили, и получилось вот так.
Хорошо.
Okay. So that's what you want to prove. And I will give you an argument. So again, so we'll look at homology groups. So proof. So the first, so we look at we consider define a Hermitian theory. With various numbers. This is Hermitian, and it's given by the formula that alpha beta. So what can I do here? I can integrate. I need one notation. So that's so I can take alpha and take the vector product with vector bar, but still this is not in the top degree homology class, it's in degree 2r, right? And they want to get a top degree homology class. But I also have this two forms, so I will denote this class by omega. This is C1 of O1. So this is if you wish, this is the first Chern class of this line bundle, or equivalently, this is the fundamental class of the hyperplane section. You have X, you have this embedding, you have a class in H2 of projector space, right? and you just take its pullback. The pullback of the class, canonic integral class in H2, generated in H2. So that's my omega. And now I want to multiply it by the power of omega, so what should I, which is, what is the power? D minus 1.
So if R is greater than D, then you don't define.
Yeah, so R is, thank you very much.
Значит, здесь точно и бета сопряженная, и HF сопряженная.
Вот это, ну, а что вот это означает? Это означает, что я, когда я так пишу, это означает, что она не линейна.
Это просто...
Это то же самое векторное пространство, только просто с...
Но форму мы представляем формы из просто HF.
Да, это просто означает, что оно нелинейно. Okay, so, but I need to correct it because, well, I want it to be Hermitian, so sort of skews. It must be, I must have the property that I want alpha, beta equal to beta alpha bar, and to achieve this I need to multiply it by a certain power of alpha. And I will leave for you to figure out what power, well, what is this power, it must be alpha. So it's similar computation, we just using this. Okay, then it has this property. So, so we have a Hermitian form, and again, if it were positive definite, we would finish the argument, right? Because definitely the F rescales this form since it multiplies omega by exactly by this constant. But it's not positive definite. Well, we have already seen that it's not positive definite even for curves, right? We use Hodge decomposition, and it was positive definite on one side, on one factor, summon, and negative definite on the other side. So that's probably something that we should add here, but that's not enough. That's not enough. Okay, maybe, so let me give you an example. Let's take x equal to p1. And let's look at this form on H2. Well, so what are the cohomologies? We already, well, this is two-dimensional space, right? Its basis is the second class of third cohomology class of P1, tensor 1, and vice versa. So if you compute this form, so if your class is real, yeah, and my basis is real, then complex conjugation does not affect it, and also we do not need any omega here, because we are already, that will be degree 2, so this will be degree 4. So what is the, so essentially in order to compute this, we need to know the intersection matrix on this surface, right? Our homologic classes are represented as fundamental classes of the two lines, horizontal line and the vertical line, right? And I want to compute the period, so I want to compute the intersection matrix. And what is it? So if I, on P1, I take the P1 times P1, I intersect two, what is the self-intersection of the vertical line? P1 times point inside P1, this is a divisor, right? What is the self-intersection of this divisor? Один. Okay. Point. Other conjectures. Zero. Zero. Yes, so every 2 points on P1 are linearly equivalent. So this divisor here is, well, all vertical lines are linearly equivalent, right? Because they are pullbacks of points from P1. And on P1, points are linearly equivalent. So I can, instead of computing self-intersection, I can compute intersection of the 2 vertical lines. So that will give me, this will give me 0. And what happens if I intersect these 2 lines? Okay, so that means that the matrix is this. And what is the signature of this matrix? Is it positive or negative?
It's neither or both.
1 минус 1. Замечательно. Signature.
Тут же можно будет сказать даже критерии Ходжа обычных.
Yes, but what we're going to discuss is precisely that, so it's an illustration. Okay, so you see that this is we are moving towards a higher dimensional generalization of the Hodge index theory. Ну, по теореме Ходжа об индексе, если вот возьмете классы в H2, которые представлены алгебраическими циклами, дивизорами, то сигнатура формы пересечения, она всегда вот один, и все остальные минус 1.
Но это если, например, мы знаем, что ядро естественного отображения из группы Пикара в H2, это
да, но, в общем, это факт. Тем не менее, это факт. Это верно. Как уж он доказывается, мы сейчас обсудим, но вот, значит, это в этом заключается теорема. Вот. Значит, very good. So, let's try to correct this.
Извините, в чем проблема?
So the problem is that our form is definitely not well, it's indefinite.
У нас нет положительной определенности.
Да. Okay. So let's try to correct. There is another problem with this form. It's not at all obvious that this is in fact even non-degenerate. How do we know that it's non-degenerate? So for curves we use Poincare duality. And what is the Poincare duality? It tells me that for any alpha I can find a class of the complementary dimension such that the integral of the product is equal to 1. But that's not an arbitrary class, it's beta times omega. It's not at all obvious that any class can be represented in this form. However, it is non-degenerate, and this is a highly non-trivial theorem, which is called the Hart-Lefschetz theorem. Okay, so I have Krogels this Hart-Lefschetz. So this is the following assertion. So let's take have any projective variety, and I look at homology group in degree d minus r. D is again dimension, so d is dimension, complex dimension. It's middle degree. And I look at the map to h d plus r, which is given by the wedge product with omega to that. So, and the theorem is that this is an Eisenhower, right? So, so particular, well, this is equivalent to saying that this is non-degenerate. Another nice corollary of this is that if I have, let's see how I want to state it, right, if k is less than d, then the map from hk of x to hk plus 2 of x, which is wedge with omega, is injective. So in particular, right, it's obvious that that's definitely false. So this map is injective. So in particular, the dimension of this space is greater or equal than the dimension of this space. Say if you have a threefold, then dimension of H1 is always less or equal than dimension of H2. Good. So now to raise this, so our goal again is to construct a kind of natural decomposition of this space to subspaces are orthogonal with respect to this form, such that the restriction of this form to each subspace is definite. However, it will have different signs. And this will complete the argument. So, and let's do this. Well, I will give a definition first. So let's define the
Of hard lefts.
what?
A proof of hard lefts.
No. It's proof of theorem. I'm not going to prove hard difference.
You return.
Yeah. So I'm going to use it. So we define subspace in homology group of X. So this is homology group in degree. So R here is any number greater or equal than 0, and this is by definition the kernel of Hg minus R of X Hg plus R plus 2. Okay? And this is wedge with omega R plus 1. You see, if I consider wedge with omega R, then by hard lefts, this is an isomorphism, so it has no kernel. But if I consider the larger power, then it may have a kernel. And now I have an exercise for you, and this is a linear algebra exercise, that, so if I make this definition, so this is a subspace, right? This is a subspace here in Hg minus R. So the exercise is to show that this hard lefts, well, implies that the entire space is direct sum of the following spaces. So first I have the primitive classes. Why do I call it primitive? So if you think of homology classes as fundamental classes of closed C-infinity subvarieties, then what does it mean to take the product with omega? It means that you take your subvariety, submanifold, and intersect this hyperplane section. So a class is non-primitive if it can be obtained by this procedure. So you have a higher by degree by dimension higher dimensional variety, and you intersect it as a hyperplane section, and then you get non-primitive. So okay, so that's what is the statement here. So you take omega p of Hg minus R minus 2 plus and so on. Okay? So the claim, so the next term will be omega squared p h d minus r minus 4. So, okay. So I will not prove this linear algebra exercise, but I will explain why it's kind of what it amounts to. So let me give you an example. So this is an exercise, and this is an example. So so let's take threefold. Yes.
Там в конце должно быть плюс h0.
Ну, зависит от отчетности. Либо h0, либо h1.
Если все яды... Да, в конце, ну, да, в конце просто.
Okay, so let's take simplest non-trivial example. Let's take h dimension d is equal to 3. So we have three-dimensional array. So we look at let's look at the middle degree homology, right? So then what we have? We have omega, and this sends h3 to h5. And we have h1 of x. So this is an invasion. This is surjection. So what is my p? My claim is that h3 of x is equal to the kernel of omega, right? Kernel of omega in this case is precisely the primitive classes, by definition, plus the image of this. Well, and this map is surjective, so it's a sort of, it's really omega times h1, right? So let's check that the hard efficiency indeed implies that we have this decomposition. So first of all, we already observed that this space is a subspace here. This map is inductive. So I need to show that the two spaces have trivial intersection. Suppose I have a class that comes in the image. Can it be killed by omega? Well, no, because the composition is the nice. Okay? We'll leave you to prove it. So now, so the next ingredient is this Hodge number, the Hodge decomposition. So we have Durand homology of X, right? And say R here, and it comes. This is a complex vector space, and it comes with a Hodge filtration. So it's the smallest term of the Hodge filtration is precisely the space of holomorphic R forms on X. Then we have something else. I don't know. Okay, so there is this is F0. And what is what is the property of this Hodge filtration? And satisfies a property similar to the decomposition that we have for curves. So, namely, so the property, the main property is that if you take Fp and intersect it with Fq bar, and then take sum of these guys over all p plus q equal to r, then the nature of the map, right? Each of this is a subspace here, so I have a map. This map is an item, and this is called HPP. Okay. So I have two decompositions of this space. One is this Hodge decomposition, which which is kind of, it really uses the analytics, well, it uses holomorphic structure. And I also have this decomposition, which is purely topological once I know the hard-Lefschatz. Hard-Lefschatz is a topological property of a projective variety, right? But it refers to multiplication by once I have class omega. It doesn't use any complex structure, right? It's a statement about Betti homology. So I have these two decompositions, and the claim is that they are compatible. So what is it? It's okay. So I need to finish, and I'll do it in 2 minutes. So what do we have? We have H. Sorry. Now when I look at degree R homology.
This is also a theorem you're not proving and you're not commenting, right?
This is Hodge theorem.
Yeah.
No, Hodge theorem I will not. So this is now what? So I claim that they are compatible. So first of all, this is direct sum all P plus Q equal to R. Primitive classes in HPQ of X plus omega times sum of P plus Q equal to R minus 2 primitive classes in HPQ and so on. Right? So let's look at this formula. So here I have...
Сейчас здесь омегу умножить, да, на это?
Да, умножить. Does it make sense? The statement. So what is this? It's by definition the intersection of this group and HPQ. So I claim that the hard-Lefschatz implies also the existence of this decomposition. All you need to know is that omega is in H11. And that is obvious because omega is a pullback from P1, from Pn. And on Pn you have only, the second degree homology group is one-dimensional and it's all H1. So once you have this, you have decomposition. And now, the last result that you need is another theorem, which is really a generalization of the Hodge index theorem. So the restriction of this form.
Сейчас, мы еще не доказали теорему.
Вообще не доказано.
Ничего не, значит, ни теорему Ходжа, ни теорему Лефшатца, ни даже вот эту теорему.
Нет, ну хотели доказать теорему вот про...
Она не будет заведена, да. Вот сейчас она будет доказана, через секунду.
Ага.
Вот. So the last result that I need is that if you take the restriction тут может быть любое число, омега A. So if you restrict this form to this subspace, the restriction is definite. Okay? So remember that our goal was to construct a decomposition, an orthogonal decomposition of this space, which is preserved by F, such that the restriction of my form to the sums is definite. Right? Once I have this, the theorem follows from the property of unitary matrices. Because my F now preserves the space, it acts here, right? And it's definite, so F rescales this form by the certain power of Q, and therefore its eigenvalues have the desired norms. So this completes the proof. I'll stop here.
Yes, so I have a couple of questions. I think in the course of the proof we assumed tacitly a couple of facts. For example, when we discussed H0 and said everything was trivial, I think that we really assumed that if X is a connected algebraic variety, then the set of its complex plates is a connected topological space. And I don't see a simple reason for that.
We did assume this. Right. Let's see. Let's see. So how to show that? Yeah. So that every component is. Well, I'm not sure that I can give you like 2 lines proof of this. That's a legitimate question. This is definitely a true fact, and this is elementary. It's not as deep as hard options.
Another thing, I think we assume that when we assign to a divisor a class in cohomology, then we assume that 2 linearly equivalent divisors give rise to the same class in cohomology, but I don't see how this follows from the definitions, because a linear equivalence is a map to P1, which is not a locally trivial fibration or anything, so it doesn't help.
A map to P1. Yes, that's a good question. On the other hand, another way of defining the first Chern class is by exponential exact sequence. So you have map from H1 x or star to H2 of x with z coefficients. This is called. So this is the boundary map for this exponential So one way to define the first Chern class of a line bundle is the following. So identify the Picard group, the set of isomorphism classes of line bundles with this group, and look at this short exact sequence of sheaths, right? Right, this is short exact because if you have a contractible set and non-Venetian functions, logarithm of something. So it's short exact. So the boundary map gives you this.
But then we have to relate h1 of xo computed in the heuristic.
Yes, so you need to do it just for Pn. You need to show that for Pn, if you take O1 on Pn, then the Chern class is computed by this recipe, gives you the fundamental class of the hyperplane.
And you don't really use that other divisors or other algebraic cycles of greater than 1 dimension give rise to the cohomology class.
No.
Okay.
Mm-hmm. Okay. So, okay, more questions.
No, I mean, of course, we also tacitly used that, the 2 definitions of genus are the same, and that the 2 definitions of degrees, you get the last semester and last year, are the same. But these these follow more easily from the first fact that I mentioned.
Mm-hmm.
Maybe something.
I will think of if I can find the simple argument for your question.
And what are the standard references for the 3 theorems that we are just stating?
The book by Griffiths and Harris, Principles of Algebraic Geometry. And all Voisin. This is really kind of the main results in Hodge theory. So it's not kind of, the proof takes, I think, first 120 pages of Davidson Harvey's book. But it's really powerful. It generalizes the Hodge index theorem.
Ну вот только не совсем, потому что бывают алгебраические циклы. Ну, в смысле дивизоры. Ну, в смысле, что...
No, as a corollary, if you have a surface,
есть то, что не приходит из алгебраических.
Right. So if you have a if your x is say two-dimensional, so if you have a surface, then so h11, the surface, is equal to p h11 plus something that comes from 0 dimension, degree 0 homology, plus just omega on x. That's kind of a special case of this decomposition. And this theorem, which is called the Hodge index theorem, asserts in this case that the pairing here is negative and here it's positive. So all algebraic classes, Chern classes of line bundles, live in this piece of the Hodge relation, right? Because it's true for classes in P, and all Chern classes of line bundles are pullbacks for some maps to P. So they all live here, and I know by this Hodge index theorem that the intersection form here is positive, is negative. So this implies a Hodge index theorem. Okay, so let's stop here. If there are no more questions, I'll see you tomorrow.
Да. Просто еще раз, ну, у меня майнер.
Да, ну, значит, ближайшие все-таки 2 недели я не хочу, вот эту неделю и следующую я не хочу сдвигать, а потом, наверное, придется, потому что у меня тоже в школе занятия начнутся очень.
Даже так? Нет, я просто хотел тебя спросить,
Ну,
ты будешь рассказывать.
Я хотел про стандартные гипотезы, про еще раз вернуться к тому доказательству для алгебраических. Я хотел рассказать про то, как вот это доказательство можно переформулировать, не используя комплексные числа, так, чтобы оно имело бы смысл над купе, над f, над конечным полем.
Понял. Слушай, я не соображу, вот историческая справка. Там гипотезы Вейля ведь доказали и без этих космологий. Ну вот что точки, как бы, что точки задаются, ну, зета-функции.
Ну,
да?
в смысле, рациональность зета-функции доказал Двор, да. Он там как так, ну, его доказательство, но оно такое очень виртуозное, но там как бы в частности он для гиперповерхностей построил теорию кристальных когмологий. Вместо летальных когмологий можно кристальные было. Хотя он слова не произносил, конечно, но оно такое, да, даже если как бы знать теорию кристальных когмологий, его вычисления совершенно нетривиально объяснить. Там как бы все хитро очень.
Ну, раз мы точки считаем, нельзя как бы и они аддитивны, как и Эйлерова характеристика, как и число Лепшица. Нельзя расслоить там на кривые, как бы вот это все использовать, эту технику, но просто не говоря слова, там как бы этальная когмология.
Ну, не знаю, но там сложно в том, что как бы не очень понятно, не знаю.
То есть уборка не так, короче.
Нет, он не использует рассеянные кривые, он для гиперповерхности, в общем-то, пишет в некотором смысле явную формулу.
Здорово. Нет, ну просто...
Оно очень интересное доказательство. оно по-прежнему очень интересно. Даже если знать все теории когомологии, все равно оно очень интересно.
Понял. Ладно, спасибо большое.
До свидания.